did the universe come from? Where is it going? Are we the sole living things in it? We're living in a remarkable period of cosmic discovery. And we're learning some extraordinary things about our universe that you'll see in this film. It was shot at the National Astronomy Observatories. You can probably tell I'm not a narrator. I'm a filmmaker. I've spent my life behind a camera, but until I took this assignment, I'd never seen anything like these cameras, the huge optical telescopes here at Kitt Peak National Observatory near Tucson, Arizona. Don Hall introduced me to them.
A telescope is just a light bucket, and the bigger the bucket, the more light you collect. This 4-meter telescope is one of the largest light buckets in the world today. Yet at the bottom of each of these buckets, there has to be something to soak up the light. At first, this was a human eye. Later, a photographic plate, similar to film you probably use in your camera today. Here at Kitt Peak today, it is a sophisticated array of television-type cameras controlled by computers. Astronomy has been an unending struggle to collect light from the faintest objects. In fact, if one took all of the light collected by all of the world's telescopes throughout history, it would be equivalent only to the light put out by a small flashlight in a few minutes.
There's a lot more to astronomy than just collecting light from faraway sources, because some very basic information about the elements that make up everything is hidden out there. Another Kitt Peak astronomer thinks about this every time she uses a telescope. Her name is Catherine Pilichowski.
You and I, the trees, the earth itself, are made of many elements that we find in the stars. In fact, these elements are produced in the stars. Tonight, I'm observing stars in globular clusters, some of the oldest stars in the galaxy. By studying these stars and comparing them with younger stars, I can learn about the processes which produce these elements.
Not only do we use optical telescopes to take pictures, they can also feed spectrographs which break light into colors much as you see in the rainbow. By analyzing the thousands of colors in the light from a single star, we're able to learn a surprising amount about it. We can tell whether it's moving towards us or away from us and how fast. We can measure its temperature, and we can find out details of its chemical composition. As a matter of fact, using this technique, we've been able to learn more about the chemical makeup of stars trillions of miles away than we know of the composition of the Earth's crust just a few miles beneath our feet. The thing about astronomy is you can never actually get your hands on anything you're studying. It's closest to theology in that respect. You can argue about things till you're blue in the face, but that's all you can do. And yet to someone who enjoys that abstract sort of science, it can be very satisfying.
When I need a new lens for my cameras, I buy it. When Kitt Peak needs a new mirror for its telescopes, they make it, grinding and polishing for years in their optical shop. They've made some of the finest telescope mirrors in the world here, precise to within 1/1,000,000th of an inch. This particular mirror may wind up as part of a new instrument that would be the most powerful optical telescope on Earth. Animation can give us an idea of how it would work. Conventional telescopes capture starlight with massive mirrors. They gather and reflect that light onto sensing devices, sometimes through a hole in the middle of the main mirror. The more light that's caught, the farther the telescope can see. Yet, the bigger it is, the more the mirror is bent out of shape by its own weight. Kitt Peak's next generation telescope may use a mosaic of mirrors in a computer-controlled array that would constantly adjust itself to maintain a perfect reflecting surface. It would be big enough to collect 14 times as much starlight as the giant 4-meter telescope that's currently king of the mountain.
Today, astronomy is one of the last of the pure sciences, with research and acquisition of knowledge ends in themselves. Yet many astronomers believe that some of the millions of stars that go to make up our own galaxy may well be surrounded by planetary systems very much like our own solar system. In fact, one of the thousands of stars you can pick out on a dark night may well be a sun to a planet very much like our own Earth, potentially capable of supporting life.
The sun is also a star, a very ordinary garden variety star, but it's the closest one we've got. So at Kitt Peak, they examine that star with a special solar telescope. It bounces the sun's image through a tunnel far down into the earth and back up to a heavily instrumented observing room. Astronomers are trying to figure out a lot of strange, short-term changes that seem constantly to be taking place on and in the sun. At Kitt Peak, the sun is one of many stars studied. But then we filmed at an observatory where they study only the sun. Sacramento Peak, New Mexico. Here, solar astronomers are making fascinating discoveries about the sun and its effect on our planet. For one thing, the sun is the biggest energy source around, and it makes good sense to learn as much about it as we can. Jack Zerker told me another reason why the sun is one of the most valuable subjects that astronomers will ever have.
In a real sense, the sun is the Rosetta Stone of the stars. It is the nearest star, and because it is so close and so bright, we can study details on its surface that we can only imagine on other stars. In this way, we learn physics that we can apply throughout the universe. We've learned, for example, that the sun is vibrating like a bell, and that these vibrations may help us to understand the interior of the sun that we cannot see. We've also learned that the sun may have stopped producing energy more than 1 million years ago and may be slowly cooling off even now.
This little solar storm is far bigger than our entire planet, and it's one of the more spectacular examples of what they see from Sac Peak.
Some stars have enormous spots that cover most of their surface. Here is a sunspot. You can see it's much smaller than the sun itself, but by studying its physics, we can understand these much larger and impressive spots on other stars. We know that changes in the sun's brightness as small as 1% would be enough to freeze the Earth's oceans permanently. We also know that when sunspots appear on the sun's surface, they produce a noticeable decrease in the sun's brightness. So one of the things that we're studying here at Sac Peak is the appearance of sunspots and their possible influence on the Earth's climate.
All of the observatories we visited are supported by the National Science Foundation. A lot of observing time at these national centers is set aside for visiting astronomers. At Sac Peak, for example, they work with a remarkable telescope that's actually a huge vacuum tube floating on a pool of mercury to let it turn freely. And when the telescope is turned, the entire observing platform turns with it. Is one star worth all that effort? Ask astronomer Dmitry Mihalis.
What we're doing here allows us to see into a star that's alive with forces that we're just beginning to understand. Forces that have a lot to do with where the universe came from and where it's going. And that's priceless.
No, that isn't the sound of outer space. It's a recording used to keep birds from nesting on these strange antennas we found in the early morning mist of Green Bank, West Virginia. They may not look like telescopes, but that's exactly what they are, radio telescopes, at the National Radio Astronomy Observatory. How do they work? I asked astronomer Robert Brown to tell me what they listen for from stars they sometimes can't even see.
This is a photograph made with an optical telescope of a newly formed star and its associated nebulosity called the Rosette Nebula. This is a picture of the same object made with the 140-foot radio telescope here in Green Bank, West Virginia. Using the radio photograph together with the optical photograph, we can determine many interesting things about this object. For instance, the red patches on this radio photograph represent areas of the nebula that are particularly hot. In addition to the temperature, we can determine such parameters as the age of the object and its chemical composition.
Our eyes can detect only a small part of the energy given off by stars, the part called visible light. But the heavens give off all sorts of energy, from high-intensity gamma rays to gentle radio waves. And because radio waves pass right through clouds of dust and gases, they tell us things that even the best optical telescopes could never see. Even car ignitions can disturb these delicate telescopes, so Barry Turner uses pedal power.
Many people think that radio astronomers look at galaxies, quasars, things like that you see in ordinary photographs. In fact, we also study interstellar molecules, and in the last 10 years we've discovered 50 such different species, many of them similar to what we also find on Earth. Even more surprising, we find that our galaxies just teeming with these molecules. With this radio telescope, we're studying these molecules. From them, we hope to learn something about how life may have formed on Earth. The signals from these molecules are exceedingly weak. They come to us from clear across the galaxy, in fact. They're so weak that if I were to take all the energy together that we've ever observed in 10 years, it wouldn't be equal to that contained in a single flea hop.
It takes incredibly sensitive instruments to detect objects as minute as molecules in space. One of the glories of the Green Bank Observatory is that most of its equipment is designed and built in its own world-famous laboratories. A huge radio telescope antenna is no better than its receiver, and that receiver has to be sensitive enough to pick up star signals as weak as a billionth of a watt. Some of those signals might be trying to tell us something, and some radio astronomers are willing to listen. Like Sebastian von Horner, who's searching for signs of life elsewhere in the universe.
These large radio telescopes are used for many purposes, mostly for astronomy, but one of the most fascinating purposes it can be used for is try to listen whether we can get some signals from outer space from other intelligent beings. There might be up to maybe 1 billion of habitable planets, and our galaxy is only one out of many. If on several of these places life, intelligence and technology have developed in a similar way as here, then there should be interstellar radio communication. We should try to seek whether we can find communication with other beings in space.
We're flying high above the world's biggest ear, this radio telescope at Arecibo, Puerto Rico, the largest single antenna in the world. Bigger than 13 football fields, it's so big that the dish can't be moved to point it. Instead, it uses the Earth's rotation as a tracking mechanism. The surface of the huge antenna is precise to within a 1/16 of an inch, and it can pick up signals from the farthest frontiers of the universe. Hal Kraft told me about it.
With this instrument, we can see objects as small as clouds of electrons and as large as entire galaxies at ranges nearly from the tip of our noses to the edge of the observable universe. So the scope and the extent of our studies here are truly enormous. The radio emissions from the heavens are reflected off this enormous dish below us and focused onto the equipment suspended far above. From the information collected in this way, we are continuing to learn more and more every day about such interesting and diverse objects as quasars, pulsars, and black holes.
quasars, pulsars, and black holes. Let's take quasars first. We're looking back in time, as well as across trillions of miles, past the planets, past the newest galaxies and ancient nebulas, the young and old stars. And finally, we come to quasars, on the very edge of the universe. Their light may have taken 15 billion years and more to reach our telescopes. No one knows what they are, but we do know that they aren't stars and that they are enormously powerful. They must have been around near the moment of the birth of the universe. We've never found anything farther away. Pulsars. They're the ashes of supernovas, star explosions. After such an explosion, the gravitational forces are so strong that even the atoms collapse. They're crushed into a ball so dense that all of what was once a huge star fits into a core just a few miles in diameter to become a neutron star. Some become pulsars because they have powerful magnetic fields that trap a beam of energy. And as the star rotates, the beam sweeps the Earth. You can't see it, but it can be picked up by radio telescopes as pulses of energy. And finally, everybody has heard of black holes. But what are they? The theory is that when some massive stars explode and die, they collapse not just into neutron stars, but contract until their volume is very small, yet their density is immense. This produces gravity so strong that not even light can escape. You can't see a black hole, but you can watch its gravity attract matter from a companion star. Donald Campbell explains another way this radio dish in Puerto Rico is used.
The Arecibo telescope not only receives energy radiated from such objects as quasars and pulsars, but it also transmits signals. In fact, it's the world's biggest radar system. With this system, we can probe beneath the cloud cover of Venus and map its surface, and we can estimate the size of the particles in the rings of Saturn.
Another astronomer, Michael Davis, found the heavens full of surprises.
I used to think astronomy was a pretty placid and gentle science, but it turns out the universe is a lot more turbulent than I thought just a few years ago. You'd think the heavens would be about as stable and unchanging as anything could be, but what we found are galaxies forming, quasars exploding, the universe itself expanding away. What's more, we're only just beginning to understand how some of these things can take place, how galaxies are formed, whether there might be life in other planetary systems.
It would take 1 million lifetimes for an astronomer to see a galaxy being formed. But for study, a computer can create a picture of it in seconds.
This is the signature of a galaxy that's half a universe away. But with the sensitivity of our telescope here, we can tell from the lines on this graph what it's made of, its general structure, just as surely as if we were there.
So we're getting signs of interference.
A radio telescope can gather information during the day as well as at night. Galaxies don't wait for dark to talk to us. Work goes on around the clock at Arecibo. Some of the journeys radio signals make take billions of years. But here's a trip we can make instantly on film. From Puerto Rico back to New Mexico, where there's a radio telescope so big that its total scale dwarfs even the Arecibo dish. This is the VLA, the Very Large Array, made up of 27 antennas that can be moved along a Y-shaped railroad track. Each arm of the track is more than 10 miles long. John Spargo explains how the dishes work together to produce some remarkable information.
With this new instrument, astronomers will be able to see into the universe further than ever before.
VLA works very much like the human eye and brain. Signals entering the eye encounter rods and cones. The rods and cones change light signals into electrical impulses which are sent to the brain. The brain then assembles it into an image. Similarly, the signals received by the 27 VLA antennas are sent to the central computer in the control building. There, after much data processing, the central computer converts these signals into a final image for the astronomer.
Dave, I just got through resetting antenna 24. Could you give me temperature readouts for antenna 5, 25, and 24 before I start back over?
Will do.
22 looks all right.
It would take a single antenna dish bigger than New York City to pick up the data that the VLA produces. It cranks out more information than any single scientific instrument in the world. These computers change the radio signals into pictures. Here's one fascinating way astronomers can watch the signals, on an image processing system. Rick Perley showed me one of the most remarkable of these new celestial maps.
What you're looking at is the radio image of a galaxy named 3C449, perhaps the most symmetric and beautiful of all radio galaxies or quasars mapped here at the VLA. This object, like other radio galaxies and quasars, is an enormous emitter of energy, more than 10 billion times the luminosity of the Sun. Yet compared to other radio galaxies and quasars, this object is a shrimp. What we think is happening is that the core is emitting gas in twin tubes at more than 600 miles per second.
5,000 miles south of New Mexico, Skip Schaller gives us our first view of another observatory.
We're over the Chilean Andes, and that's Cerro Tololo Inter-American Observatory down there. Well, most astronomers live in the northern hemisphere. Most of the stars are here in the south. The southern hemisphere is the only place from which we can look into the Milky Way, the center of our own galaxy. And if we ever learn what's going on in there, we'll know how stars and galaxies were born throughout the universe.
Cerro Tololo Inter-American Observatory is located high in the Andes Mountains of Chile. The air is super clear and steady, giving the astronomers what they call good seeing. They can study stars here that can't be seen from North America. Cerro Tololo has 8 telescopes, and they're usually all working every clear night of the year. This is the smallest, and the biggest one is the largest in all of the southern hemisphere. 2 resident astronomers who use it are Francois and Linda Schweitzer.
The one thing that sets us apart from all other creatures is our curiosity about the world we live in. And the curiosity of the astronomer extends to the borders of the universe, whatever they might be. Yet the more we learn, the more we find out we don't know.
Actually, astronomers don't look at galaxies, but at the history of those galaxies. What they see now took place millions or billions of years ago. That's how long it's taken the light to reach us.
Galaxies not only give birth to stars, but some of them also seem to have a life of their own. Right now, I'm working on a remarkable galaxy that seems to be a celestial cannibal. With this telescope, I'm observing how it is swallowing a smaller victim galaxy and how it is using the material of that galaxy to fuel the tremendous energy that's pouring out of its nucleus, probably out of a black hole.
The heavens are a huge laboratory where we can watch the universe go through almost every stage of its evolution. And what we're learning out there can increase our understanding of our own planet.
I'm studying galaxies to try to determine their masses. And with this knowledge, we hope to be able to determine whether the universe will continue expanding or whether one day it will collapse.
Francois and I both fell in love with astronomy when we were children,
And years later, we and a lot of astronomers like us have become so involved in the high technology, data reduction, computers, and electronics, we feel removed from that original romantic feeling that we had about astronomy. So sometimes it's good for us to get out among the stars like this so that we don't forget what this science is really all about.
Today, our horizons stretch not only to the stars, but to the beginning of time. We've already solved many of astronomy's mysteries, but those basic questions remain. Where did the universe come from? Where is it going? Are we the sole living things in it?